I just had a question. Like when you solve the partial fractions and
Hmm.
you get like so I got like p over 1 minus p equals est after I was trying to solve for c.
You got p over 1 minus p equal e to the st.
Yeah, sta.
Sure.
That was after I exponentiated
Right, right,
the
right. Yeah.
and
And now
so
how do you solve for p, right?
yeah. So do I just leave it like that?
No. So here's the thing. So you're right in that a lot of the time there are going to be differential equations where we solve and we can't actually isolate like y or p or whatever it is, right?
Hmm.
Here we can. Usually the way so there's a couple of different ways you can attack this. One option is to just take the reciprocal of both sides and then multiply, and then cross multiply. But it's kind of the same. I'm just going to multiply both sides by 1 minus p. So I'm trying to solve this. I get p equal to 1 minus p times e to the whatever. Distribute this. So then you've got p equal to e to the whatever minus p times e to the whatever. Add this back over here. So p plus p times e to the whatever equals e to the whatever. And then factor out the p. I'm running out of room here. Sorry, 1 sec. I don't want to erase the stuff I already wrote. Um, so then, right, so, so factor out the p, so you've got p times 1 plus e to the whatever equal to e to the whatever. And finally, you can divide by this, you get p isolated as e to the stuff over 1 plus e to the stuff.
Oh, okay. Yeah, that makes
Totally
sense.
works. Yeah. So whenever you're solving a differential equation like this, and you get to the place where you have like y over 2 plus y equals something, or right, where you've just got like you've got a linear rational, like a rational function where the top and the bottom are both linear. So you got something like some AP plus B and some A, like right, a multiple of P plus a constant over multiple of P plus a constant. You can totally just multiply this over, distribute, bring all the P's to one side, and then solve for P.
Okay, so when I'm solving for a, like the what you know how because the what I got was the a was times the e to the st.
Not so sorry. It's not E to the STA. It's A times E to the ST,
Yeah,
like this.
yeah. So
Okay,
that was like the constant after I
right.
exponentiated.
So then at the end here, it'll instead of being what I wrote, it's just A times E to the ST over
Okay.
1 plus A times E to the ST.
Would you recommend me what's it called to solve for the constant? Um at
What do they tell us the initial conditions are?
yeah.
What are they?
Oh, they're p of 0 equals 1/3.
Sure. I would probably no. I think yeah. Let's see. So where's the easiest? So somewhere in here is going to be the easiest place to solve this. So you're trying to solve for t, right?
No, for a.
Oh, sorry, for a. Um, it's probably going to be easiest to solve actually at the beginning. So yeah, plug in. Was it 1/3 for p?
Mhm.
So 1/3 over 1 minus 1/3 is 2/3 equals a e to the 0, right?
Mhm.
So 1/3 over 2/3 is 1/2. So it looks like your a value is 1/2.
Okay. I was just making sure because
Yeah. So then the nice thing is, so your answer is going to be 1/2 e to the st over 1 plus 1/2 e to the st, but then we usually multiply the top and bottom by 2. So your answer would actually be e to the st over 2 plus e to the st.
okay.
Kind of cool. Yeah, that's a good question. All right.
Thank you.
You're very welcome. Yeah. So just for everyone who came in, we are just talking about part D of problem 1 on worksheet 7. So if you get to the place where you get p over 1 minus p equals a e to the st. You can solve that for p by multiplying both sides by the denominator, distributing, bringing all the p's to one side, factoring it back out, dividing. Yeah, and yeah, it's really pertinent to think about when you want to solve for a. In this case, usually you want to solve for the constant when it's kind of easy, right? And in this case, it's probably easiest right at the beginning when you like if you tried plugging it in here and solve it for a, you have to kind of work backwards to get back to just a. So you want to try and solve for your constant when it's fairly isolated or easy to isolate. Yeah, all right. So I'm gonna erase that. So I wanted to talk about what she was talking about in class, although, so actually that's just a few things. I do want to do some more integrating factor examples because I do think it's important to practice that. But I did want to talk about what she was talking about in class today, the direction fields. I want to show you guys a couple things, then we'll kind of go back and do some first order linear / integrating factor, same difference. And then we'll move forward and we'll maybe talk about Euler's method for a minute. Two things. One, you guys have your next short test on Wednesday next week, correct? Yes.
Yeah.
Cool. So my plan, I think, is to try and do what we did last time and to give you guys a practice test the first half of class on Monday. Which means I'll have to figure out what to write it on. And then the second half to go over it. And the other thing I wanted to ask everybody, and you can message me privately if you prefer to message me privately if your answer is this. I'm curious if this would be a good weekend to not have a quiz, since you guys have a test coming up. If you want the quiz, I'm happy to write one for you guys to have more practice. But if you feel like you've got enough on your plate and you don't want me to give you guys a quiz, let me know. So my plan currently is to not give you a quiz. But if people say they want to have a quiz, let me know. And you can let me know privately. Maybe it'll be an optional quiz if you want to have a quiz. So if anyone wants to have a quiz, let me know, and I will do it. But if nobody wants a quiz, I will not post one for you guys. Okay. All right. I'm hearing a lot of no quiz, but yes, practice test sounds good. Okay. Again, if anyone says they want a quiz, it's also fine. I can make it optional. So I want to talk about this. So she was talking about this particular equation, not that this one's special for any reason, but since you already saw it in class, I wanted to kind of show you a few things. So let me, so first of all, so we've got dp dt equals p times 1 minus p times q minus 5p. And they said p was between 0 and 1, and y was between 0 and 1 as well. Or no, sorry, and t was between like 0 and 8 or something. What I want to show you is that you can, there are ways. So I just Googled Desmos direction field to see if I could do it on Desmos, and you can. But it's not like something they have programmed in. It's something people have kind of made workarounds for. So let me show you a couple of them, and I'll put them in the chat as well. I'll also probably post them on camera so you can see them. But let me show you what I mean. So is this the right one? That's not what I wanted to do. Sorry. Yeah, let's go over here. So I've got 3 options for you. So the first one is not the best for this problem, and here's why. They're only giving you the little marks every 1 unit. Right. So if we zoom in a little bit, I know this isn't the right one, but so that's why it's funky. There's an X marks there. Sorry. So they've started us off with the differential equation y prime, right? G of xy is dy dx. G of xy is 2x over y. That's not what we want. We want this one. We can't use p's and t's because this is in terms of x's and y's. So we're going to replace our p's with y's and our x's with, well, there aren't any x's to write, so we're fine. So I'm going to have y times 1 minus y times 2 minus 5y. And you'll notice it's not super helpful. And the reason it's not super helpful is because the kind of the step between each mark is a whole 1. And if you remember the graph she was doing, it was a lot of marks in between 0 and 1. So this one just isn't fine enough. I still think this is a good tool to use, You can also, you can't change that really, but if you click on this part here, you can move this point here. So that point there, you can move it around and it'll show you what the slope of, right? So it's kind of cool. If you zoom in a little bit more, right, you can kind of, whoops, let's zoom out a little bit. So over here in the 0, 1 realm, right, we can totally be like, oh yeah, I'm going to move it this way. Notice if we move it horizontally, the slope doesn't change, which is what she was saying, right? Doesn't matter what the t value is for this particular one, since the derivative doesn't depend on t or x. If you just move it left or right, the slope isn't going to change. But if you move it up or down, oh yeah, the slope is going to change. So that's kind of cool. I do like this functionality in this one that someone created. I haven't seen this in other places, which is kind of neat. If you recall, the line y equal to 0.4 was kind of where it went from being a positive slope to a negative slope. So we see that if we are above that, the slope is negative. If we're below that, the slope is positive. Whoops, between 0 and 1 anyway. So that's kind of cool. Let me, and again, I will put these all in what's the word for, in Canvas as well. Oh, that's interesting. Sorry, that's what I wanted. Apologies. So question, can you guys see my chat? I mean, nothing that matters really. There's not like anything terrible there. I don't think you can, but I'm curious. Can you see the chat that I am pointing at right over here?
No.
Yeah. Okay. I mean, that makes sense, right? Like that's a wise programming choice, but there's nothing terrible over here. But let me go ahead and give you guys that so that you can totally use that if you want. So you could, right, if you're trying to do some other thing like, right, just something fun like x plus y, then we can zoom out and be like, oh yeah, it's giving us this cool kind of direction field where again, each of these little lines means if, for example, if x is, in fact, let's go over to this point right about there. If x is -3 and y is 4, then we get a slope of +1 because -3 plus 4 is +1. And we can totally see that. And the slope there is for sure +1. It's unfortunate. It's certainly don't tell you. Like, I mean, I know we can see it here, but it'd be kind of nice if they actually said what the slope was. Oh well, it is what it is. So that's one option to use. It's pretty good. Here's another option, which is nicer in some ways. So let me show you. So this is giving us, again, they're writing it as f of xy. So again, right, f of xy is your derivative dy dx. So we are going to plug in the same equation just to see what it looks like. Now, if you look at this, it looks super wonky, right? It's like, whoa, what's going on? So I would like to adjust some of these parameters. And there's a lot I can adjust. So I can basically, x1 and x2 are how far left and right it goes. So I want to go I want it to start at 0. And I don't really want to go that far to the right. 54 is way too big. Let's go like, I don't know, like 10. Sure. And same thing for y. We only want y, right? For that graph she was doing in class, we had y between 0 and 1, or p between 0 and 1. So let's go y down to, I guess, right, up to 0, and y2 down to 1. Okay, let's go. Well, okay, that's a little crazy. Let's zoom in. Oh, look, that looks pretty good. So this kind of shows us, right, what's going on. And you can also, this one, you can also change how long the little lines are, right? You can slide this left and right. And you can also, you can change like how far they are spaced apart. I don't love this one so much. If they space them like way out, it's kind of weird. But you can kind of see, yeah, there's your direction field. And right, here's the line y equals 0.4 right there. Above it, they're all sloped downwards. Below it, they're all sloped upwards, like we saw. So this one, you have to kind of be a little bit more comfortable moving things around to get what you want. But I think this is a useful tool as well. Here is the link to it if you want it. And then finally, so here's the other thing I like about these two. These two in Desmos, I mean, this one is nice if you're, this is a pretty reasonable, like usually -10 to 10 on either axis with a step of 1 is a fairly reasonable kind of way to plot a direction field. But the nice thing about both of these is you can then draw a graph in there. So I was working on one, where'd it go? Sorry. So I was working on, oh, where did you go? Oh, I know what it was. It was, we'll come back to that one actually. But the nice thing here is like, if you knew what a solution looked like, you could actually literally type it in, right? I don't know what the solution to this is, but we'll come back to this. Lastly, there's this one from GeoGebra, which doesn't have the ability to like, you know, graph another thing on top of it, which might be like, maybe that's a solution. I don't know. It's probably, it kind of looks like almost solution. Maybe it's more like, I don't know, 2 to the x. Could be, probably not, but whatever. But the cool thing about this last one here is that you have a lot more fine tuning abilities. So if I plug in the same differential equation one more time, y times 1 minus y times 2 minus 5y. Press return. So it gives you the whole, and I don't know why it's giving me this. I don't want that there. It's giving me a solution at a particular point, which seems, why is that? I don't know. I don't know what this is. I don't know what that's out there. Anyway, let's turn that off. So again, this is giving me the direction field. Now I can definitely change my x minimum, my x maximum, my y minimum, my y maximum to maybe like 1.2. You can see, oh yeah, look, this is looking a lot like what she had, right? At 1, you're doing this kind of deal, going down, and then up, down here, going up. And you can change the density of them. You can make them less dense, right? We didn't zoom in, right? We still have the same x and y scale. We just are drawing less of them per kind of region. And you can also make them longer or shorter. Ooh, really short, ooh, really long. So I feel like this is pretty great as well, personally. So, right, if you want to kind of, I think this is probably the nicest of them. The only downside to this one is you don't have the functionality of being able to then like plot another graph on top of it, which is too bad because that would be really lovely. But here's the link to that one as well. Again, you can find all of these by just Googling like how to graph a direction field in Desmos or GeoGebra. So not that you shouldn't practice being able to do it by hand a little tiny bit. No one ever wants you to do this by hand. But here are some tools to help you kind of do it not by hand. All right, we will circle back around to this. I will post a quiz. It will be totally optional and it'll probably have like 2 not too hard questions. Probably 1 first order linear question and 1 something else. I haven't decided yet. Okay, so let us go ahead and do a first order linear question or 2 just to practice. And then I should also take a look at you guys. Real quick, like, oh, sorry. Okay, yeah. Yeah. So let me, sure, that's good. Okay, cool. Let me grab, where is the problem? Yeah, that seems fine. Sure. Okay, let us look at this example. Yeah, should I do that real quick? Sorry, I'm just trying to think of something here. So here I want to show you guys one thing first. So let's say I had this differential equation, y prime minus 6xy, let's do plus 6xy equal to xy. Xy, let's do x. Sure. Okay. So here's what I want you guys to see about this. Is this a first order, so is this an integrating factor problem? differential equation, or is this a separable differential equation? Well, the answer is both. You could totally do this as an integrating factor problem, right? It's already written in the correct format. It's y prime plus a function of x times y equal to another function of x. That's the standard format you have to write it in before you can do an integrating factor. But I will also point out, you could totally do this as a separable differential equation. So to do it as a separable, you have to bring everything to one side and y prime on the other side. So to even think, is it separable, I have to rewrite it as y prime equal to x minus 6xy. And then observe that we can factor out an x. So that y prime is equal to x times 1 minus 6y. Well, look, this is separable because the right-hand side is a function of x times a function of y. So if you can do it this way, it's usually easier to do it this way. It's totally legitimate to do it the integrating factor method, but your life is going to be easier if you do it this way. So I'm going to say dy dx equals x times 1 minus 6y, and then do the usual thing, right? Dy over 1 minus 6y equals x dx. So then we integrate this, we get negative 1/6 the natural log of the absolute value of 1 minus 6y. Why the negative 1/6? Because of the negative 6 there. Equals the antiderivative of x is x squared over 2 plus c. And then you can solve for y. Let's see, solving for y, kind of a pain. You would get multiplied by negative 6, so you get the natural log of the absolute value of 1 minus 6y equals negative 6 times 1/2 is negative 3x squared plus c, right? Negative 6 times a constant, still a constant. And then let me give us an initial condition as well. Let's say, I don't know. Let's say our initial condition is that y of 0 is equal to, I don't know, 7. So we're going to exponentiate both sides. This side is going to be the absolute value of 1 minus 6y equal to e to the negative 3x squared plus c becomes times e to the c becomes times a new constant k. Right, that k there is e to the c. And then this is, well, actually, so this is where you should drop these absolute values, because the constant there will be positive or negative as necessary to figure out what's going to happen. Then we're going to plug in our initial conditions. So y of 0 is equal to 7. Maybe I picked a crazy number. That's all right. So 1 minus 6 times 7 is equal to k times e to the 0, which is just 1. So k is negative 41. So I get 1 minus 6y equal to negative 41 e to the negative 3x squared. And then we solve for y. So I never want to do the work at the end here. So solving for y, subtract 1. So negative 6y equals negative 1 minus 41 e to the negative 3x squared. And then divide by negative 6 to get y equals positive 1/6 plus 41 over 6 e to the negative 3x squared. Now that did seem like a bit of work. It's definitely less work than doing it using the integrating factor. So I really want to stress, if you have a differential equation, even if it's written in the way that looks like you should use an integrating factor, you might want to double check. Can I isolate y prime and write the other side as a function of x times a function of y? Basically, can I factor out one variable from it? If you can, that's usually the easier way to go. So just something to be aware of. Well, let's look at the problem where we can't do that. So let's look at something like this. Tangent of x times dy dx plus y equals sine squared of x. So this is definitely looking like the integrating factor form. You have, well, kind of, right? It's not exactly, right? To have the right form, again, you guys really want to make sure you get this ingrained. The correct form is going to be y prime plus function of whatever your other variable is, x or t usually, plus some function of x times y equal to some other function of x. That's the form we have to have it in to be able to use the integrating factor. To get from this to something like that, we always have to divide by what's multiplied by your y prime. So divide everything by tangent. So dividing by tangent, I'm going to have dy dx plus I'm going to have 1 over tangent of x, which is cotangent of x, times y. And then I'm going to have equal to sine squared of x divided by tangent of x, which I should definitely simplify. So sine squared of x divided by tangent of x, I think that's also cotangent. Let's take a look. Sine squared divided by tangent is sine squared divided by sine over cosine. If you divide by a fraction, you flip and multiply. This is sine squared x times cosine x over sine x. Oh no, it's wrong. It wasn't cotangent. Cancel a sign there, a sign there. It's equal to sine of x times cosine of x. So sine squared x over tangent x, we should definitely rewrite as sine of x times cosine of x. Or if you prefer, you can write it as 1/2 of sine of 2x. I don't know if I prefer that yet. Right? Maybe some other things are going to happen, but we definitely know that we need to kind of manipulate this. All right, so now we're going to do the integrating factor thing. So we're just going to multiply the whole equation by I of x. Integrating factor. So I'm going to have dy dx times I of x. I kind of prefer to write y prime. I kind of like it better. Plus, and I'm going to write this in a slightly different order. I'm going to write it as y first times cotangent of x times I of x. And on the right hand side, I am going to write it as sine x times cosine x. So sine x cosine x times I of x. Sorry, I'm kind of a little close there. Okay. By the way, stop me if you have questions. The whole reason we multiply both sides, everything by I of x, so that we can then say that this left-hand side is the derivative of y times I. So I'm gonna say this every time because you should think of it every time. Gosh, that's really good. Sorry, my computer's really like glaring on that one spot on the board there. Hopefully that helps a little bit. Hopefully you can see that a little bit better now. The derivative of y times I is y prime times I plus y times I prime. Okay. So the derivative of this, is equal to this, and it's still equal to the right hand side. So it's still equal to sine of x times cosine of x times I of x. Okay, now here's the important part. We're going to integrate both sides. The integral of the derivative is just the thing. So I'm going to say that y times I of x is equal to the integral of sine of x times cosine of x times I of x dx. And then I might as well, since I'm already there, we're trying to figure out what y is, right? We have a differential equation, dy dx. We want to know what the function y is as a function of x. So we're going to have that y is equal to 1 over the integrating factor times the integral of sine of x times cosine of x times I of x. And don't be dumb like I was once upon a time. You can't cancel those I of x's, right? You have to actually find I of x, multiply it through, then integrate, and then after we've integrated, we can divide by the other integrating factor. Okay, the only thing left to do, really, I mean, well, that's not true. The things left to do are to find the integrating factor and then do the integration. So, of course, there's not enough room. Let's go to the other side. So if I have Euler's method, do you guys know is Euler's method fair game for your quiz for your short test on Wednesday?
We talked about it in class. So
Yeah, I saw that today. So, but is stuff today going to be possibly on the quiz or the short test on Wednesday?
yeah, it's everything from volumes to what we learned today.
Okay, volumes up to today. That'll help me write it. Okay. So we're trying to solve this differential equation. The I prime is equal to cotangent of x times I. So I prime of x equals cotangent of x times I of x. Or preferably, di dx equals cotangent of x times I. I don't really need the I of x. So then I'm going to separate variables. I'm going to have di over I equal to cotangent of x dx. Cotangent. Oh, yeah, all right, cotangent. So then we're going to integrate both sides. By the way, solving for the integrating factor always plays out this way. You always are integrating di over I and getting the natural log of I. Every single time. It's going to equal, do you guys know what the integral of cotangent is? It might be easier if you thought of it as the integral of cosine of x over sine of x. You could do a u sub, where u is equal, okay, let me ask you guys, if I'm going to do a u sub for cosine over sine, should I pick u to be the thing on top or the thing on the bottom?
The bottom one?
Yeah, the bottom, right? Because the thing on the bottom is the thing that's stuck. So if I pick u equal to sine of x, our derivative is cosine of x dx. We could have picked u equal to cosine because the derivative is essentially sine, it's negative sine. But the problem is we don't have a sine times dx. We have a 1 over sine. We have a cosine times x. So this is the right choice. So this becomes the integral of du over u, which is just the natural log of u, which is just the natural log of sine of x. So the integral of cotangent of x is the natural log of sine of x. Great. And again, we're ignoring the absolute values and the plus c's. Then we get I equal to sine of x. Or I of x if you want. Okay, great. So we're going to throw that in here and here. So here's what we're going to have. Let me write it on the other side still. So that means we're going to have that y is equal to 1 over sine of x times the integral of sine times cosine times sine, or sine squared times cosine. Okay. I'm going to integrate this. Again, u substitution. In fact, the same u substitution we did for the other one. U equals sine and du equals cosine x dx. So if u equals sine and du is cosine, it's not, this is like a coincidence, it's the same u substitution. But if u is sine and du is cosine x dx, there's my du, there's my u squared. So I end up getting 1 over sine of x. The integral of u squared du is u cubed over 3. So I get u cubed, so I get sine cubed. plus c. Very important, because then we distribute the 1 over sine. 1 over sine times sine cubed is sine squared x over 3. 1 over sine x times c is c over sine x. And that's your answer if we don't have initial conditions. Kind of funky. Whenever you're doing this integrating factor thing, your answer always is going to have at the end the constant c divided by the integrating factor. Right? You never just have like the constant c. It's always being divided or multiplied by the thing that's out in front here. Okay. Let's see. Oh, time is flying by. So let's go ahead and circle back around to what's the thing I want to say? Yeah, I'll try and okay. To direction fields and Euler's method. Let's see, I know I had things to say about these. These are probably better dealt with by me showing you things versus trying to draw things. Again, I will point out that Grant has some great pictures on his website. So let's look at this. Let's look at, yeah. So let's say I want to maybe draw, yeah, we'll try draw. We'll draw one, and then we'll see how you can do it better. So let's say I want to draw the direction field for dy dx equal to y times x plus 1. Okay. So, and I'll go up to like, I don't know. Well, I'm gonna cheat. So typically you want to kind of draw marks every unit is what I usually, when I'm drawing it myself, I draw marks every 1 unit. So 1, 2, 3 is probably more than enough. Okay, things to look for. It's very easy to look for what makes this equal to 0. So what makes this 0? Well, y equals 0 would make this always 0. And x equals -1 would also make this always 0. So here's what that means. It means on the line y equals 0, the derivative is equal to 0, meaning the slope of the tangent line is equal to 0. So along y equals 0, all of my little slopes are little horizontal lines, which I know is not super easy to see, but you guys kind of see them. It also means that along x equal to -1, so let me actually draw. I'm drawing all these little points here because these are the points where I'm going to maybe put a little tangent line. Okay, too many points, right? It's a lot of points to have to deal with. So, but at x equals -1, the derivative is 0. So all along x equals -1, so my tangent line is 0. But then after that, you're kind of stuck like plugging in points. So like, for example, if x equals 0, so if x equals 0, dy dx is just y. So when y is 1, the slope is 1. When y is 2, the slope is 2. When y is 3, the slope is 3. When y is -1, the slope is -1. That looks a little too steep for -1. Right? So you can maybe kind of see that this is going to be tedious. Because then you go over and say now for x equals 1, right? So when x is 1, the derivative is y times 2. So at 1, 1, it's going to be y times, or sorry, 2 times 1. So it's going to be, right, steep. And then here, when x is 1 and y is 2, you're going to get 2 times 2, which is 4, so even steeper. And then it's going to be even steeper. And then here it's negatively steep, negatively more steep. So I think you can maybe see that it's a terrible process to try and draw this by hand. But you can totally see, so going back to, I'm going to go to the one that I think I would probably use most often. I would probably use this one with the colorful lines. Let me share my screen again. So let's delete some stuff. I don't need this anymore. I don't need this anymore. I'm going to change this to, what do we got here? Y times x plus 1. Cool. Now, it would be nice. I don't think we have it, right? So, so that's kind of right. I've got my, you can see, whoa, geez, oh my God, sorry. Getting a little wild there. Okay. That seems reasonable. So if you look at the line x equal to -1, well, look, yeah, every tangent line for x equals -1 is a horizontal little snippet. And the same is true for y equal to 0. By the way, these lines where the derivative is always equal to 0, I should really say these curves, because they don't have to be straight lines. These curves where the derivative is always equal to 0, these are called nullclines, or I feel like there might be another word for them. Nullclines, maybe zeroclines. I don't know. They're not called isoclines. Isoclines are where the derivative is equal to a specific value. But these are nullclines where the derivative is always equal to 0. And they are nice to identify because they make it easier to kind of see what the graph looks like. And then okay. I don't know where this line is coming from here. I must have done something funky. I don't know. Anyway, I did. Yeah, there's a weird line there. Another interesting thing about this is if you know what the solution is. So I found the solution to this differential equation. It's not hard to find. I wrote it down here. So if your initial condition is 0, 1, meaning you're starting at the point 0, that's that, like, what's that line? That's the y-axis. Okay, smart, James. So if we're starting right there, 0, 1. Right, so moving this point over to right there. I suppose it's easier to do it this way. Right, so if I'm right there, well, here, now you can't always find the solution easily, but if you know the solution, which I do, the solution is the following. It is y equal to 2e to the x squared over 2 plus x. Maybe I missed it by 1. How did I get 2? 0, 1, no, 0, 0, why? I don't know why I have a 2 there. I think I was trying to make it more interesting. There. So check that out, right? There is the solution to the differential equation with this initial condition. And if you follow the graph here, anywhere you're looking at the graph, the tangent line, the slope of the tangent line is the slope of the direction field little tangent thing. So that's kind of the idea, is that if you kind of, you can see what a solution looks like without actually knowing the solution by trying to just kind of draw it out and be like, okay, well, if I start here, I'm going to kind of go down to the right, and then kind of just go this way. And eventually I'm going to like do something like that. So we could totally just see this by, I think, let's see here. Right, so like, look, there's a different, like there's maybe the initial condition where we start at this point up here, like -4, 6, for example. If my initial condition was y equals 6 when x equals -4, approximately, right, you would end up with this graph instead. Kind of neat. But look what happens if you change your initial condition to like 0, -1. Then you get a totally, I mean, a similar looking, but totally different result. So kind of cool. Again, the point is you can use the direction field graph to kind of see, like, if you started here, for example, and let me turn this off for a second. If you started right here, going left to right, it would be like, okay, I'm going to go this way, and then I'm going to kind of turn that way, and then I'm going to kind of turn that way. And that's going to be kind of this like downward opening looking parabola-ish sort of thing. It's not actually a parabola, but it kind of has that look. So neat. Yeah, okay, last 5 minutes. Yeah, so let me talk about Euler's method for the last 5 minutes here. So I think she did a very good job of talking about what it is. I remember the first time I learned Euler's method, which was when I was teaching 17B for the first time. I was like, this is super confusing. I have no clue what's going on. It takes practice. Once you look at it for a little bit, you can be like, oh yeah, this makes sense. So here's the idea. Oh, geez, come on. I think we can maybe, I might need an extra minute or two at the end here to kind of relate it back to the direction fields. So let's say we have this. We have the, I'm going to use X's so I can relate it back. So we have the differential equation, y prime equal to x plus y squared, which I don't think is particularly easy to solve. I don't think we actually have the tools to solve this because it's not separable, right? You can't get dy divided by something with y because you can't divide that over without leaving y over here. And it's not first order linear. It is first order. It's not linear. So we can't use the integrating factor method either. Darn it. Okay, so what we're going to do instead is we're going to say, I want to estimate what y of 2 is equal to. So estimate y of 2 by, sorry, remembering. Okay, so estimate y of 2 using steps of h equal to 0.5 and y of 0, initial condition y of 0 equals 1. All right, so here's what we know. We know y of 0 equals 1. And we're going to try and get to y of 2. So let me make my graph a little bit bigger. So here's what we have. We know that y of 0 is 1. And here's what we're going to do. We're going to find at every step of 1/2 the new y value. We're going to say, okay, I know that right here at this point, I know right there that the slope is y prime at 0, 1. Well, great. I guess I can write it this way, f of x, y. Let's write it that way. The slope is f of 0, 1, which is 0 plus 1 squared, which is 1. So here's what we know. We know that at this point, the slope of the tangent line is 1. What we're going to do is we're going to say, okay, well, I'm going to go over a step of 1/2. If I'm going over half and my slope is 1, I'm going to go up half as well. So I'm going to go over half, up half. There's my y1. So this is y0 right here. This is y1 right here. Now the way we actually calculate that is by doing this equation, which I've never could remember. It's y sub n plus 1 equals y0 plus h times f of, it's either t0 y0 or x0 y0 or xn yn, depending on, sorry, not y0, y previous, and then xy, xn yn, or t if you're using t's. So right, all that is your previous y value, 1, plus your run times your slope to get your rise, right? Rise equals run times your slope, or slope equals rise over run. So right, you're finding the rise and you're adding that onto your previous y to get your next y. So in this case, y sub 1 is y sub 0 plus h times f of 0, 1. Which ended up being 1 plus 0.5 times 1. Okay, so the way we find the next one is we do the same thing. We start here at the point, let's see, so this next point here is 0.5 comma 1.5. And we say, okay, at that point, what's the slope of the tangent line? So we use the differential equation, and things are going to get ugly now. So f of 0.5 comma 1.5 is going to be 0.5 plus 1.5 squared. 1.5 squared is 2.25, so it's going to be 2.75. So that means at this point, the slope of the tangent line there would be 2.75. Right? So a much steeper slope, right? So I go over 0.5, I'm going to go up like 1.375. Sorry, and I'm trying to make this look kind of nice. 1, 2, 3. So from, let me just, so my next point, and I think I'm going to stop here because we're definitely out of time. So y2 is going to be y1 plus h times f of 0.5 comma 1.5. Right, so you're just finding the slope of the tangent at the new point, your new x and y value. The slope there happens to be 2.75. We're going to multiply it by h, which is 0.5, and we're going to add it to the previous one, 1.5. And we're going to end up getting, sorry, where's my calculator here? That's actually literally written over here. We're going to get 2.875. So about right there. So what we're doing is we're saying from this point here, sorry you guys, I know I'm out of time. The slope of the tangent line is much steeper. It's 2.75. And then we're going over a distance of a half. So I don't really need all this other stuff here. Right? So for the first half, for the first 0 to 0.5, we use this tangent line. And then for the next 0.5 to 1, we use this tangent line to get from here to here. And then we do the same sort of thing to get the next one to be even steeper, and then the next one to be even steeper. That's kind of the idea, is that you're basically, every time you're refining your calculation, you're saying, oh, from here to here, I'm going to just use the next tangent line. So let me show you this picture. So here's the picture of the work that Grant did on this handout. In fact, let me throw that in the chat as well, so you guys can all see it yourselves later on if you want. Here it is in the chat. But the whole idea basically, right? From here to here, we're just like, there's the tangent line, got the new point. Here to here, there's the line whose slope would be, what the slope of the differential equation gives us from there to there. And this other graph here is the actual graph of the solution. So we're seeing here like, oh yeah, our tangent line approximations are just getting us closer and closer to that. You could also, so circling back around to the direction field, if we actually were to graph this on the direction field, I wish I had a, sure, let's look at this one. So y equal to, I'm going to use x instead of t. And then let's go, sure, minimum 0, maximum, let's go to 2.5. Y minimum 0, y maximum like 8. Ooh, or maybe bigger. Let's go 10. And then, right, density, sure, more dense. Length a little bit longer. So the idea here, right, is that we're starting at 1, which my y scale is a little too big. Sorry, 1 second. Let me move this to 5. So we're starting here at 1, and then we're using this tangent line, and we're using, so right there, right, if that's our point, we're then saying, okay, I'm going to go over this way for a length of 0.5, and then we get to like right here, and then we use the tangent line there. So the tangent line here is in this direction. I'm going to go in this direction for 0.5 until I get to like right here, and then I'm going to go in that direction for 0.5, right? And so obviously I'm going to go off the chart here, but that's the whole idea, is that you're using the slope of the tangent at that particular point to give you your next over and up. and then slope of the tangent of the next result to give you your next over and up. This is how you do the calculation, right? It's your previous y value plus your step size, also known as the run, right? If you're thinking rise over run, it's your run times your slope at that point. And then you just keep doing that until you get to what you want. All right, hopefully that makes a little bit of sense. Sorry, I've talked so much over.